You ever look at the steam coming off a boiling kettle and just wonder? How can something that seems so gentle, so simple, be powerful enough to change the entire world? Well, today, we're going to pull back the curtain on the incredible engineering that did just that, harnessing simple steam to kickstart the Industrial Revolution. And that's really the core question, isn't it? It just seems impossible. The same exact physics that makes a kettle lid rattle has to somehow generate enough raw force to move a massive 200-ton machine of solid steel. It sounds like magic, but stick with me, and by the end of this, you'll see exactly how it works. So, to get to that answer, we've got to take a step back and look at the journey. It wasn't one single invention, but a whole series of breakthroughs that unlocked steam's true potential. It all kicked off way back in 1712 with a guy named Newcomen who had this really clever idea to use steam to create a vacuum. But the real game changers? That was James Watt, who made things way more efficient, and then the absolute bombshell in 1800, the high-pressure steam engine. That one invention changed everything, allowing engines to get smaller, way more powerful, and, crucially, mobile. And that leads us straight to the icons we know, like the locomotives and tractors of the 1860s. All right, so to really get our hands dirty here, we're going to zoom in and look at a classic traction engine from the 1860s. You can think of it like an early tractor. The reason we're looking at this one is because its engine is basically a smaller, easier to understand version of the absolute beast inside a locomotive. So it all boils down to these key parts working together in perfect sync. You've got the firebox, which is just burning coal to get things super hot. That heat boils water in the boiler, creating a ton of high-pressure steam. Then the slide valve, which is kind of like the brain of the whole operation, directs that steam into a cylinder. The steam expands, pushes a piston, and that motion gets transferred by the flywheel to, you guessed it, the wheels. It's this beautiful mechanical chain reaction. And that chain reaction is like the engine's heartbeat. It's this constant, elegant four-step cycle. First, steam blasts in and pushes the piston one way. Then, the valve cleverly shifts, lets out the old, used-up steam, and immediately lets in a fresh blast of high-pressure steam to push the piston all the way back. This back-and-forth push-pull motion is what creates that constant, reliable power. Now, this brilliant design has a name. It's called a double-acting cylinder, and it was a huge leap forward. Why? Because the steam is actively pushing the piston in both directions, out and back in, so you're getting twice the power for every single cycle. Oh, and you know that intermittent psh sound of the used steam getting vented out? That's what gives a steam locomotive its iconic chug-chug-chug sound. Pretty cool, right? Okay, so we've got the mechanics down, we see how the parts move. But that still doesn't quite get us to the bottom of our big question. How does this simple cycle create enough force to move literal tons of steel? Well, the secret is all about pressure. To really get this, just look at the difference. Those early engines, like Newcomen's, were clever that they actually relied on the atmosphere outside the engine to do the work. They were limited by the natural pressure around us. The high-pressure engine completely flipped that idea on its head. It generated insane amounts of pressure inside the engine that pushed out against the atmosphere. And here's the key takeaway. Its power was no longer limited by nature, but only by how strong you could make the steel that contained it. So how'd they do it? How did they create all this crazy pressure? Well, it wasn't magic, it was just physics. 3 simple tricks, really. First, you boil more water to cram more steam molecules into the same sealed space. Second, you heat that steam up even more, making each molecule zip around faster and hit way harder. And third, you shrink the container, confining it all into a small, tight volume. You put those 3 things together, and the pressure just skyrockets. And now we get to the payoff. Let's finally put some numbers on this and see just how much force we're really talking about. And trust me, these numbers are absolutely staggering. Let's go back to our little traction engine. When you get the pressure inside up to about 90 pounds per square inch, the total force pushing down on its piston, which is about the size of a dinner plate, is nearly 3 tons. Let that sink in for a second. 3 tons. To help you visualize that, here's an amazing analogy. That's like taking 2 entire cars and balancing them on a single dinner plate. That is the kind of force being unleashed with every single stroke of that piston. Okay, but that was just the tractor. Now let's scale it up to a full-sized locomotive. Here, the pressure is more than double the tractor's, and the piston itself is much bigger. The result? A truly mind-bending 58 tons of force on one single piston. That's like the weight of 40 cars. And here it is, the final piece of the puzzle. A locomotive doesn't just have one of these incredibly powerful pistons, it has two. One on each side. So you're effectively doubling that insane amount of force. And that is how you move a 200-ton train. So, you can see, the steam engine did so much more than just move trains. It moved the entire world into a completely new era. But, like any truly world-changing technology, its legacy is complicated. The engineers of the Industrial Revolution, they were focused on physics and efficiency and making things work. And they were brilliant. They gave us incredible progress, modern conveniences we take for granted. But they had no way of knowing that burning all that coal would have this deep, lasting effect on our planet's climate. And that's a challenge that, of course, we're still dealing with today. And that leaves us with one last really big question for ourselves. It kind of forces us to look around at our own most celebrated inventions right now, things like AI or genetic engineering, and just wonder, what are the unforeseen impacts? What are the long-term consequences that we right here, right now, just can't see? It's a pretty powerful reminder that every great innovation reshapes the world in ways its creators never, ever could have imagined.